And this is chapter 10, the shapes of molecules. If we just think about a simple molecule like water, very simple molecule, H2O, I bet you that everybody who's hearing the sound of my voice, has seen water written like this before, where you have sort of this angle between the two oxygen-hydrogen bonds, like this. There's some kind of angle here, and there's a good reason for that. There's a good reason why people write water with this shape. In fact, we say that water does have a shape. We say that it has a bent shape, and I'm not kidding. That's what we call it. We say water is bent. Okay, it's got this bond angle here. That bond angle is around 104 degrees, very close to 104 degrees. And what we're going to be doing in chapter 10 is we're not immediately going to be looking at the shapes of molecules, but we're going to get there in chapter 10. And we're going to embark on some strategies at the beginning, namely Lewis structures, that will enable us to determine the shapes of molecules. So that's where we're going in this chapter. And if you're wondering, why would I want to know the shape of a molecule? Couldn't I just look at a model or something and figure out the shape of a molecule? Well, what's great about the shapes of molecules is that if you understand, and when you do understand, and you have to understand the shapes of molecules, it will help you to predict sometimes physical properties, melting points, boiling points, and things of that nature. So without further ado, let's go on here. It says, how do we convert a molecular formula into a structure? This is just kind of an introduction slide. I'll kind of show you the quick and dirty way to make a Lewis structure. The first thing that you'll do is you'll count up the total number of valence electrons in the molecule. So let's start with NH3. Since we looked at nomenclature earlier today, can anybody tell me the name of NH3? It's got a common name that I asked you to memorize way back in the nomenclature days. Does anybody know the name of this molecule?
Ammonia.
Yeah, absolutely. It's ammonia. Thank you. Perfect. This is ammonia. Okay. Now, how many valence electrons does nitrogen have? Okay. If I look at my periodic table, and you're going to need one. If you don't have a periodic table with you right now, make sure you grab one. A nitrogen is in group 5A. And so nitrogen has a total of 5 valence electrons. So we're going to use those in writing out our structure. How many valence electrons does hydrogen have? Well, hydrogen is the first element in the periodic table. Its electron configuration is 1s1, and therefore hydrogen has only 1 valence electron. But in an ammonia molecule, we have a total of 3 hydrogen atoms. So we're going to take that 1 valence electron and we're going to multiply it by 3. And 1 times 3 equals 3. Now, how many total valence electrons do we have? We have 5 from the nitrogen plus 3 from the 3 hydrogens. That gives us a total of 8 electrons. Okay? The next step is going to be this. I'm going to tell you a rule that I want you to remember for the rest of your life. Hydrogen, the first atom in the periodic table, can only ever have 1 bond. Okay? It can never have 2 bonds to it. So if you think about the H2 molecule, we looked at the structure in previous chapters, H2, there's only 1 bond. So that tells us that nitrogen is going to have to be bound to each one of the hydrogens. So I'm going to draw a single line to each one of those hydrogens. Again, if you don't follow me, the reason why I'm drawing a line is because a line represents a bond. In a bond, in a covalent compound, it represents the sharing of electrons. This is not a trick question. How many electrons are represented in this bond that I have the red arrow pointed toward? How many electrons are shared in a single bond? Exactly, there's 2. So I have 2 electrons here, I have 2 electrons here, and I have 2 electrons here. Now again, what rules have I invoked? I've invoked the rule hydrogen can only have 1 bond, and in a bond, there are 2 electrons. How many total electrons did we have? We had a total of 8 electrons, valence electrons, because we make Lewis structures made from valence electrons. Okay, so if I have 6 total electrons, how many do I have left? I'm going to have 2 electrons left over. Where could I put those 2 electrons? Does anybody have an idea where they might go? And that might be a tricky question, but you can give it the old college try. Where would those? So somebody says 2 dots on top of nitrogen. And those people are right. And if you're like, what are you talking about? Why would you put 2 dots on top of nitrogen? Let me explain it to you, okay? Let me explain to you why. Because in these 3 bonds, in these 1, 2, 3 bonds, each one of them has a pair of electrons. So a pair is 2. 2 times 3 bonds is 6 electrons. We have 8 valence electrons to use up in our Lewis structure. So the last 2 electrons we're going to put on the nitrogen, okay? Here's another thing I want you to know, is that remember, in a covalent bond, right? All 3 of these bonds are covalent bonds. In a covalent bond, it's the sharing of electrons. So this hydrogen sees 2 electrons, right? It has the 2 electrons from this bond. How many electrons does hydrogen need to fill its valence shell? It needs 2, right? Because when hydrogen has 2 electrons, it has the same electron configuration as helium, which is the nearest noble gas. So that means that all 3 of the hydrogens have a duet. Now, what about the nitrogen? The nitrogen has 1, 2 electrons, 3, 4, 5, 6, 7, 8. What's the closest noble gas to nitrogen? Is neon. And so now nitrogen's valence shell is full. It has a complete octet. Okay? It has the same number of electrons as neon does. Give me a thumbs up if you just follow me on even 60% of the rationale that I just went over. Even if you just follow me 60% of the way. If you're better than that, that's good. But even if you just follow me part of the way. Let's try another example, because the best way to learn Lewis structures is just by looking at nothing more than examples. So let's try CO2, carbon dioxide. Okay, how many valence electrons does carbon have? Well, carbon is in group 4A, so it has a total of 4 valence electrons. Oxygen is in group 6A, so it has a total of 6 valence electrons, but there's 2 oxygens. So that gives me 12. That means that my total is 4 plus 12, which equals 16 valence electrons total. That's what I'm going to use to make my Lewis structure. Now, there's a rule that's going to come up on the next slide, and it applies most of the time, not all the time, but most of the time. And the rule is we put the least electronegative element in the center in a Lewis structure. What does that mean? If I look at the electronegativity of carbon, its electronegativity is 2.5. The electronegativity of oxygen is 3.5. So we're going to put the carbon in the center. So here's where I'm going to start with my Lewis structure. I'm going to put a carbon in the middle, and I know it's got to have bonds to oxygen. There we go. Who can tell me in this little structure that I have, which isn't finished, how many electrons have I used up? How many have I used up? I've used up 4, right? Because there's 2 in each bond. So 16 minus 4 gives me 12. That means I have 12 left over. Let's just throw them on here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If you look at this structure, you might think, hey, now the oxygen has a complete octet. Look, the oxygen see 1, 2, 3, 4, 5, 6, 7, 8. Hey, that's good. It's got the same number of electrons as neon, right? It's got a complete octet. Let's look at this oxygen. 1, 2, 3, 4, 5, 6, 7, 8. Beautiful. What's the problem? The problem here is the carbon does not have a complete octet. It only sees 1, 2, 3, 4 electrons. That's a problem. We want it to have a complete octet. If you're thinking, well, come on, you already used up all the electrons. There's 16 electrons here. What can you do? Let me show you. Remember, if I erase a pair of electrons on the oxygen on the left, 2 electrons can make a bond. Look, now the oxygen on the left, look at this oxygen. It still has 1, 2, 3, 4, 5, 6, 7, 8. It's got a complete octet. Okay, this oxygen over here has 1, 2, 3, 4, 5, 6, 7, 8. It's got a complete octet. Let me ask you a question. Does the carbon have a complete octet? In the structure that I have drawn here? Yes or no? The answer is no. The carbon only sees 6 electrons, one from each bond, and there's 1, 2, 3 bonds. So what can I do? That means that I'm going to have to keep moving this around. I'm going to move those 2 electrons on the oxygen on the right and make another bond. Now let's take a look. I see that both of the oxygens have a complete octet, right? They both have 1, 2, 3, 4, 5, 6, 7, 8 electrons. And the carbon has 1, 2, 3, 4, 5, 6, 7, 8, 2 electrons for each bond. That means that all of the atoms in carbon dioxide now have a complete octet. And this is a perfectly legit Lewis structure. Give me a thumbs up if you follow me on that one. CO2. All right, great. Thanks. Good. Okay, then. I'm going to speed it up a little bit. Who can tell me how many valence electrons are in water? Valence electrons. Somebody says 8. Somebody says 10. Somebody else says 8. Somebody else says 8. Let's do it. Oxygen has 6 valence electrons. Hydrogen has 1 valence electron, and there's 2 of them. So that means 6 plus 2 gives me 8 valence electrons. Okay? Now, again, I told you that there's a general rule that you put the least electronegative element in the center, but there's an exception for that. When you have hydrogen, hydrogen can only have 1 bond, right? Only ever. And so hydrogen has to be on the outside. And so let's do it. We're going to put our oxygen in the middle. We'll put our 2 hydrogens. We've used up a total of 4 electrons. The hydrogens are done. They're toast. They cannot have more electrons than 2, right? 2 electrons and 2 electrons. They both have a complete duet. So if I have 6 electrons left, I'm going to put 1, 2, 3, 4 like that on my oxygen. And now let's look. The oxygen has a complete octet. 1, 2, 3, 4, 5, 6, 7, 8. And that's going to be the Lewis structure of water. Now, I'll be completely honest with you. Last spring, when I taught this class, I used this as my first slide. Okay, this was my first slide last semester, but I decided that this semester I would start right off the bat with a few examples, because I find that if you see a few examples first, it helps you understand the rules better when you see them. So here are the steps broken down for you into a 5-step method as to how you draw Lewis structures. Let's start. The first thing that we started with was a molecular formula. NH3, CO2, H2O, whatever. Then we placed the atom with the lowest electronegativity in the center, unless, okay, except H, right? Hydrogen, that's always got to go on the exterior because it can only have 1 bond. The next thing is you add A group numbers. For your A group number, you add or subtract the number of electrons. So for example, oxygen is in group 6A, so you add 6 valence electrons. Hydrogen is in group 1A, you add 1 valence electron. If you have a carbon, it's in group 4A, you'd have 4 valence electrons, so on and so forth. Then you draw single bonds, and remember that each single bond represents what? 2 electrons. We can put here, there are 2 electrons in every bond. Okay, get the clarity. 2 electrons in every bond. Okay, anyhow, then depending on, in step 4, you're going to distribute the electrons so that each atom has a total of 8 electrons, unless you're dealing with hydrogen. Hydrogen only needs a duet. It doesn't need an octet. Everything else is going to want to have 8 electrons, right? This is what we call, the octet rule. Now, I'll be completely honest with you. We're going to start looking at exceptions to the octet rule probably next class, maybe today. So there are plenty of exceptions to the octet rule, but let's not focus on that right this second. If the central atom lacks an octet, after you complete steps 1 to 4, you start moving electrons around until the central atom gets an octet. And that's what I did in this example here with CO2. You remember me moving the electrons around? And if you're wondering, well, Mr. Dion, well, that means I'm going to have to use trial and error to figure out some Lewis structures. You know what I would respond to that? Yes. Okay, yes. Sometimes you will have to use trial and error, and you will have to have an eraser. I wouldn't be messing around with Lewis structures with, with ink. I would use a pencil. Okay, well, let's try another example. That's a pretty blank slide. Let's try an example. Nitrogen trifluoride, okay, a covalent compound. Now that you've seen the rules and you've seen me do it, this is where it would be a lot of fun to be together in the class. But we're going to do it the way we can, which is over Microsoft Teams. First, I'll ask my students, can anybody tell me how many total valence electrons we have in NF3? Let's see if anybody can nail it right away. Somebody says 23, somebody says 8. Okay, we get some different answers here. Let's take a look. Well, nitrogen has a total of 5 valence electrons, right? Nitrogen is in group 5A. Fluorine is in group 7A. And so that means that fluorine has 7 valence electrons, and there's 3 of them. So 7 times 3 gives me 21. So that means my total is 5 plus 21, which equals 26 valence electrons. Okay, I saw a lot of answers. A few people got it. Do you follow me just on the number of valence electrons? Nothing more than that. So 5 plus 3 times 7. Okay, good. If you need a calculator, grab it. Okay, if you can't multiply 3 by 7 and get 21, you're a little rusty on your multiplication, no problem. What was the next rule? The next rule is that we're going to place the least electronegative element in the center. Nitrogen has an electronegativity of 3. Okay, nitrogen electronegativity is 3.0. Fluorine is electronegativity is 4.0. And so we're going to put the nitrogen in the middle. We're going to draw lines. I like to space them out as much as possible, like this. Okay. And if you're like, well, hold on, Mr. Dion, I wrote this. I put them like this. I don't care. Okay? I just want you to get the right answer, my friend. Okay. I don't care what the angle is yet. We're going to worry about the shapes more later on. Okay. What was the next rule? We're going to start adding electrons to the atoms on the outside, the 3 fluorines, so that they have a complete octet. Before we do that, though, I have a question for you guys. How many electrons have I used so far in this structure? How many electrons? Not a trick question. Exactly. I've used 6. I've got 3 bonds. There's 2 electrons in this one. There's 2 electrons in this one. And there's 2 electrons in this one. 2 plus 2 plus 2. I know this is complex math, but 2 plus 2 plus 2 is 6. Okay, I'm kind of being silly there. But we've used 6 electrons. And so if we take 26 and we subtract 6 electrons, we're left over with 20 electrons. We've got a lot of work left to do. So what we're going to do now is we're going to fill up the octets of the outer atoms. Let's do it. 1, 2, 3, 4, 5, 6. Now the fluorine has a complete octet. If you don't believe me, look. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we're going to do the same thing to the other 2 fluorines. We're going to put 3 pairs on each of the fluorines like that. Now I've used up 4 times 6. Okay, right? Let's count slowly. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I've used up a total of 24 electrons. Total. But I had 26. So that means I've got 2 electrons left. Let me delete all that spinach. Okay, I've got 2 electrons left. Where are they going to go? Who can tell me? Let's see, I got my face like closer to my screen. Yeah, somebody says a lone pair on the nitrogen. Absolutely, you're going to put them up here, right? Because you had 2 electrons left over, and now nitrogen sees what? It has 1, 2, 3, 4, 5, 6, 7, 8. Every atom's got a complete octet. Everybody's a winner, right? There's your Lewis structure. Give me a thumbs up if you're like, boy, I tell you what, you locked me in a room for a few minutes, and I give me some time, and I could figure this out. I could figure out Lewis structures. Great. Okay. You know what? The only way to get better at Lewis structures is to keep practicing. There's the solution. But let's look at some rules before we keep going. You've got to know these rules. Let me put the word in here for you. Maybe I'll put in here memorize. I'll be bold. Memorize these rules. These are going to be your best friend. Okay, when you're doing Lewis structures, if you know these rules, it's going to help you a ton. Let's go through them quickly. Okay, put my memorize up here. Okay, so hydrogen atoms form, it should say form one bond, not for one bond. Anyhow, they form one bond like that. Okay, carbon always has 4 bonds, no exception. If you don't believe me, think about CO2. This is our Lewis structure for CO2. Count the number of lines. 1, 2, 3, 4. Carbon always has 4 bonds. In fact, when I teach nursing organic chemistry, the first thing I tell them when I walk in the room, I don't say my name, I don't say the class, I just walk in and I said, I probably all have your attention and you won't forget what I say in the first 20 seconds of class. Here it is. Carbon always has 4 bonds. Blanket statement, you know. And trust me, those students never forget that. They'll remember it for the rest of the year. Nitrogen atoms form 3 bonds. So nitrogen is going to form 3 bonds like this. Okay. Don't believe me? It usually has 3 bonds in a lone pair. Don't believe me? Let's go back here. Cha-cha-cha. Okay. I know you believe me. Where was I? Oxygen atoms form 2 bonds. So oxygen usually has 2 bonds in 2 lone pairs like that. Don't believe me? What about water? Right, the oxygen had 2 bonds in 2 lone pairs. Or you can have a double bond to oxygen like this with 2 lone pairs like that. Either way, halogen atoms almost always form 1 bond. Fluorine always does. So fluorine will only ever have 1 bond and 3 lone pairs like that. Chlorine, iodine, bromine, similarly. Okay. There are some exceptions. Okay. Somebody says, what about carbon monoxide? That's a Lewis structure that involves charges. So we'll get to that in a little bit. All right, we're not there yet. We're looking at uncharged molecules. So we've already done these 3. So with that in mind, let's look at this one here. Let's look at difluoromethane. So that's this compound here. You don't have to be able to name that. I'm just thinking out loud. Carbon, so we have CCl2F2. Okay, who could tell me how many total valence electrons there are in this guy? CCl2F2. Not a trick question. Not a trick question. Total number of electrons. Somebody says 32. Somebody else says 32. It's a big number. Yeah. Okay. I got a bunch of people saying 32, and they're all right. Okay. This molecule has 32 electrons. Don't believe me? Carbon is in group 4A, right? Chlorine and fluorine are in group 7A. So that means that carbon has 4 electrons. Chlorine and fluorine both have 7 electrons. We have 2 chlorines and 2 fluorines. So that means 7 times 4. 7 times 4 is 28 electrons. 28 and 4 gives you 32 valence electrons. Now, we've got the total number of valence electrons. We're rock solid on that. What are we going to do next? Well, if we go back to these rules, here, we learned that the halogens, like fluorine and chlorine, almost always form 1 bond, and carbon almost always has 4 bonds. The carbon atoms, always have 4 bonds. And so that means, just based on those rules, we've got to start like this. We're going to start like this. We're going to have a carbon atom with 4 bonds, right? It's going to have 2 bonds to fluorine and 2 bonds to chlorine. If you did this, if you're like, well, Mr. Dion, I wrote something similar. I wrote this, and this, and this. That's the same thing. It doesn't matter. You're like, what? I wrote this, and this, and this, Either way, these are all the same. Okay, those are all the same. So let me delete these 2. Okay, they all mean the same thing. They're just a carbon with 1 bond to each, the fluorines, and to each chlorine. And so at this point, actually, let me redraw that. I could do better. Oops. Delete. Redraw it. I have a carbon bound to 2 chlorines, bound to 2 fluorines. So far, I've used up 8 electrons. Don't believe me? 1, 2, 3, 4, 5, 6, 7, 8. 32 subtract 8 gives you 24. That means I got 24 electrons left over. All right, before I keep going, I have a question for you guys. Are there any atoms in here that have a complete octet in what I've got drawn thus far? Do any of these atoms have a complete octet? Yeah. Liv says it's carbon. She said carbon has a full octet. And she's absolutely right. In fact, all my students are saying carbon, right? The carbon sees 1, 2, 3, 4, 5, 6, 7, 8 electrons. The 4 halogens don't have complete octets, right? They only see 1, 2 electrons. And so we're going to take those 24 electrons. Look, 24 divided by 4 is 6. That means we can put 6 electrons on all of these, like that. Let me ask you this. Do all of the halogens now, do they all have a complete octet? Yes or no? Do they have a complete octet? Yes, they all have a complete octet. Absolutely. You guys are silly. Anyhow, yes. Let me ask you another question then. The bold question, is our Lewis structure complete? Is it done? Is it good? How would you rate this Lewis structure on a scale of 1 to 10? I'd give it a 10. I would give it a 10 out of 10. I would give it a 100. Somebody gives it an 11. Wow. That's pretty high praise for this Lewis structure. Anyhow, you'd be completely correct. Okay, there's nothing wrong with this Lewis structure. It's done. Stick a fork in it. It's over. Okay, so I'm going to redraw that Lewis structure up here, and I'm going to let you think about the next one while I'm doing that. I'll let you guys give it the old gander. Next one. Okay. And Camden, this is going to partially address some of what, not entirely, but some of what you were getting at, because we have charges in carbon monoxide. And we have PCl2 minus. Okay, so we have a -1 charge. For every negative charge, we're going to add a valence electron. And for every positive charge, we're going to remove an electron. So phosphorus has a total of 5 valence electrons because it's in group 5A. Chlorine has a total of 7 valence electrons because it's in group 7A. We multiply that by 2, so we have 5 plus 7 times 2, but we have the negative charge, so we're going to add 1 more. So that's 14 plus 5 is 19, plus 1 is 20 electrons. Remember, you add 1 for a negative charge, so we add 1 electron, right? Electrons are negative. Okay, now chlorine can usually only have 1 bond. So let's start with our phosphorus in the middle. Phosphorus is less electronegative than chlorine. So we're going to start with the phosphorus in the middle. The chlorine's on the end. Right now, we've used up 2 electrons. We've got 18 to go. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So there we go. Now you can see that the 2 chlorines have complete octets. Don't believe me? Look, 1, 2, 3, 4, 5, 6, 7, 8. Good. Let's look at the other chlorine. 1, 2, 3, 4, 5, 6, 7, 8. Also good. Now let's look at the phosphorus. The phosphorus has 1, 2, 3, 4, 5, 6, 7, 8. Okay, so everything here is good. And I think I'd have to go double check our book. Okay. I'd have to go double check our book, but I think that what she does is this. She'll put a bracket like this, and then she puts a minus charge. I want to do one better than that, okay? I want to put the negative charge where it belongs. And for that, you need to know what's called formal charge. So I'm going to teach you something brand new. Are you ready? Who's ready to learn something new? Formal charge. Anyone? Nobody wants to learn something new? Okay, one person. Okay, so one person's ready to learn something new. So, okay, formal charge is on an atom. This is how we do it. We take the number of valence electrons, we subtract sticks, not strix, I don't even know what that means. We subtract sticks, and we subtract dots. Okay, this is a stick. Okay, This is a dot. Okay, so let's start with chlorine. Let me delete my stick and dot first. Chlorine has 7 valence electrons. So I take 7, I subtract 6 dots and 1 stick. That gives me 0. That means there's no charge on the chlorine. This chlorine has 7 valence electrons. It's got 1, 2, 3, 4, 5, 6 dots. And it's got 1 stick. That gives me 0. What about the phosphorus? Phosphorus has 5 valence electrons because phosphorus is in group 5A. 5 subtract and 2 sticks. What does that give me? 5 minus 4 minus 2. Negative 1. That's right. It gives you a negative 1. So that tells you that the negative charge is actually on the phosphorus atom. And walla walla bing bang, that is one beautiful Lewis structure that we can take to the bank. All right. All right. Somebody's asking me about bent structures. Again, we haven't gotten to the shapes yet. We're just looking at Lewis structures. In order to understand molecular geometry, which deals with shapes like tetrahedral, bent, trigonal pyramidal, trigonal planar, octahedral, square base pyramidal, seesaw. In order to understand all those shapes, we have to understand Lewis structures first. So that's what we're doing right now. Let me show you the solution to this problem, the one we just did. And again, this is what the book does right now. You're like, oh, Mr. Dion, you're teaching us stuff we don't need to know, like this formal charge thing. Ha ha ha. Don't worry. Formal charge is going to show up in this chapter. Generally, we want to make formal charges of the central atoms 0 if we can. Not necessarily. Not necessarily. Depends on the Lewis structure. Okay, well, let's keep going. This is a pop-up question. I'll give you a second to think about it before I ask you. It says, what's the correct Lewis structure for iodine trifluoride? Let me give you a minute to think about it. It's hard for me to not talk, but I'll give you a minute to think. Let's see. Oh boy. Oh wow. I got all kinds of cool answers here. I got E and B and all kinds of stuff. What's look. All right. Says the correct Lewis structure for iodine trifluoride. Well, both iodine and fluorine are in group 7A. And 7A, that means they've got 7 valence electrons, and we have a total of 4 atoms with 7 valence electrons. That means we have 28 electrons. So we're going to start with our iodine in the center. We're going to draw bonds to our fluorine like that. And we know that fluorine can only ever have 1 bond. In fact, fluorine will only ever have 1 bond and 3 lone pairs like this. So now we've used up 8 times 3, which is 24. So if you've used up 24 electrons, that means we've got Mr. Dion needs to wake up here. We've got 4 electrons left over. The only place that they can go will be here, okay, on the iodine, which would mean that the answer is C. And if you're thinking, whoa, hold the phone, Mr. Dion, you made a big mistake, man. there's a big problem here because your fluorines are good. You got 1, 2, 3, 4, 5, 6, 7, 8. But now your iodine has too many electrons. Let me show you, okay? It's got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, the thing is that iodine is in the 5th period. And for elements that are past the 2nd period, you can have what's called an expanded octet. So let me write that in here. Elements past 2nd period, okay, can expand octet. Okay, like that. Okay, so they can have an expanded octet. So the fact that iodine has 10 electrons isn't that big a deal. And if you're wondering, well, how can it expand its octet? It's because elements that are past the 2nd period have d orbitals available to them, and so they can put the electrons in d orbitals. So the answer is C. All right, there we go. Somebody's asking about A. There's a big problem with A. Can anybody tell me what the problem with A is? Major problem here. It doesn't have enough electrons, right? In A, you don't have enough electrons. You got 8, 16, and you got 17, 18, 19, 20, 21, 22. You got 24 electrons, so you're missing 2 electrons. That's the problem there. Here, you've got don't have enough electrons, and here you got too many electrons. In fact, you know what? This is the only one that had the right number of electrons. Why did I go through that big explanation when the answer was the only one? There we go. Yeah, somebody also said fluorine is sharing, has 2 bonds, and it can't do that. So that's also a big no-no. Thanks for pointing that out. Yeah, fluorine can't do that. Okay, fluorine only ever has 1 bond. All right. Kind of fun stuff. Anyhow. Here.